All right, does anybody know the incomplete nuclear equation for one possible reaction that takes place in the core of a nuclear reactor is uranium-235 plus a neutron yields lanthanum 139 plus molybdenum 95 plus 2 neutrons plus something. And the first question is, state the name given to this type of nuclear reaction. Is there anybody out there brave enough to offer what they put for their answer so I can either confirm or deny? Sean. That's incorrect. So the triple alpha process was the fusion reaction that we looked at yesterday. Okay, so you looked at your notes, you thought, well, maybe this is it. Okay, but the triple alpha process is specific to 3 helium nuclei. Those are alpha particles combining to form carbon. That's the triple alpha process. So that very specific reaction that we looked at yesterday is triple alpha. So that's incorrect. You didn't earn the mark there, but you can still earn half a mark for a test correction. So as long as you correct it here, you can award yourself half the mark. So keep that in mind, everybody, as we go through this, make corrections. Don't tell me your score though is like, I got 100% unless you earned every mark the first time. I expect everybody will have everything corrected by the time we're done with this. So yeah, you'll earn all the marks by then, but don't give yourself full credit for corrections. Give yourself like either half credit or only a quarter of the credit. You can be, more harsh than that if you want, but you can take the whole mark away. You can say, no, 0. I'm not giving myself any credit for test corrections. I'm going to hold myself accountable, and next test, I'm going to get it. It's up to you, but you can award up to half credit for corrections. So anybody else? And thank you for offering the answer. It's okay to be wrong. It's like, hey, is this it? No, it's not. That's okay. Maybe somebody else had something else that's wrong, and they're just not brave enough to offer it. Anybody? E-learners, unmute your mic. YouTube, type it down in the chat. Maybe you know what it is. That doesn't help us here now in class, but maybe the future, other people studying this stuff. Maybe they're studying it for their A-level physics, not necessarily for astronomy purposes. So the essential question on the board is a big clue. Okay, it chose that question for a reason. Did anybody sort of say, well, this looks like a massive nucleus that's splitting to form fragments? So this here would be, everybody can see it down there. I think we even heard a student in class. Everybody said it together. It was on the tip of everybody's tongue. Let's all say it. Fission. So this is an example of a fission reaction. So yesterday we looked at fusion. This is fission. So splitting apart a big atom into smaller pieces. Okay, is fission. Fusion is putting together smaller things to make sort of something bigger. So carbon's bigger than helium. 3 heliums make a carbon. Triple alpha. That's fusion. This is fission. Complete the nuclear equation. So, we talked about having the proton numbers conserved. So you can't sort of lose protons, this bottom row, and the nucleon number up top has to be conserved. If we look at the proton number, we got 92 on the left side of the yield symbol. So we started with 92, and neutron doesn't have any protons. And then we've got 57 plus 42 is 99. So we have extra protons on this side. We need to sort of cancel out 7 of them, right? So it's 92 equals 92. So we need something that has a -1 charge, okay? In other words, has a proton number of -1. So it's not like, oh, it's an antiproton. No antimatter here. This is just going to be an electron, all right? And so an electron is not a nucleon. So its nucleon number is 0, okay? Its atomic number, if you will, is -1. Its proton number is -1. So it's going to be sort of the thing that subtracts away. We need 7 of them, right? So just like there's a 2 coefficient in front of these neutrons, you put a 7 coefficient in front of this. And so to complete the nuclear equation, to earn these 2 marks, you would need to have filled in sort of those dashed lines with this symbol. 7 electrons. And then again, this nuclide symbol just tells us nucleon number, proton number. So it's 0, -1. And that's always going to be true for an electron. And this is identical to the reaction we looked at on Tuesday. Okay. So like if you took notes on Tuesday, go ahead and take a look at it now. It's like, oh, I had it right there, of course. It was right there in my notes. So, take good notes. Just as a historical point, this is a possible reaction that can occur in a nuclear reactor. So we can fission uranium, and like down in Port St. Lucie, there's a nuclear power plant. I've taken students on field trips there before. It's a really fun sort of, they got an energy encounter, kind of fun projects that you can do. But there's a guy named Leo Szilard that said, if we could release more neutrons than what we capture, so it's kind of like, this uranium captures this neutron and then it fissions, but then it releases 2 neutrons. And he said, well, if those neutrons could then crash into more uranium, we could start this chain reaction that would weaponize this. And so Leo Szilard was the one that said, if we get neutrons out of this type of reaction, then we can make, an explosive. And so he's the one that convinced Einstein to write the letter to Roosevelt. Leo Szilard figured out this chain reaction. He was first trying to do something with fusion until he heard about fission. So in 1939, this reaction was sort of first hypothesized as being the one that could lead to nuclear sort of weapons, and it is. So this was the first nuclear bombs were made from actually plutonium, which is if you can bump up uranium by a few, then it's plutonium. So sort of by capturing neutrons and keeping them stable, you get plutonium, and then that's what they made the first apocalypse. Anyway, that's just an aside. All right, so 2 marks for this, 7 electrons. The mass defect for the reaction is 0.223 unified atomic mass units. So we had previously had to add up all the mass over here, add up all the mass over here, do the subtraction to find this answer, the mass defect. This question is a little bit friendlier. It's like saying, hey, we did all that for you. We did that calculation. Trust us that it's 0.223 U. And now all you have to do is convert this into joules. All right, so we'd start with 0.223 unified atomic mass units. This was an open note quiz, so I'd expect you to have this value somewhere in your notes, because without it, it's impossible. Like if you don't know that a unified atomic mass unit is 1.66 by 10 to the negative 27 kilograms, you didn't take good notes, or you're absent the day or absent-minded the day we went over it, and you'd be stuck. You wouldn't be able to sort of take the calculation any further. So if I have this many unified atomic mass units, that's sort of missing, right? And so missing sort of on this side, we're liberating energy when we fission this uranium. So it fissions back, things heavier than iron tend to fission back towards it. And both the molybdenum and the lanthanum have a higher binding energy per nucleon than the uranium. So they're more stable, which means we release energy in this. So we liberate energy, and this is when they control this reaction, when they control how these neutrons, crash into more uranium, they do that with what things called control rods. Then you have a controlled, you can use it for nuclear power, like in a nuclear power plant. So that's sort of what they do there. All right, so we need to take this number times this number. So this times 0.223. Let me show you how I type this in my calculator. I happen to have the document camera on, so you usually see that. So 1.66 times 10 raised to the negative 27. In my calculator, I have to hit 27 and then toggle it to negative. And when I hit equals, it's like, that's the number I want to see in my calculator. That's, the unified atomic mass unit. So now it's times 0.223. And so this is the mass. It's not the final answer. This is the mass, 3.7018 by 10 to the negative 28 kilograms. Hopefully you're able to calculate this many kilograms, and then you said, well, how do I turn mass into energy? And this was kind of the focus of last week, and Einstein's famous paper, does the inertia of a body depend upon its energy content? And indeed it does. So we're just going to plug in this mass, 3.7 by 10 to the negative 28 kilograms. To get joules of energy, we need meters per second squared times kilograms. We're allowed to use 3 by 10 to the 8 meters per second to approximate C, or you could use the more precise value. So since I already have this number in my calculator, I can multiply it by, I'm going to type it in like this, open parentheses, 3 by 10 to the 8, close parentheses. So that's the speed of light, but I want it squared. So that's the speed of light squared, roughly 9 by 10 to the 16. So now when I hit equals, it will do the multiplication. And so that's my final answer, 3.3 by 10 to the negative 11 joules. Okay. Did anybody get that? Anybody get these 2 marks? Anybody out there? That's a tough one. Okay, so try to give yourself feedback and say, where did I go wrong? It's like, oh, of course, I didn't know this. I had it in my journal. I just forgot that that's the thing that I needed to get the math. Or maybe you forgot to, square C. So whatever, sort of wherever you went wrong, try to sort of give yourself immediate feedback and say, okay, this is where I went wrong. This is what I'll do next time so that I correct it. And make the correction right now for yourself, and then you award yourself, the partial mark. Suggest two forms of the energy released in this reaction. So this is, again, an identical question to what we talked about on Tuesday. Does anybody have that in their notes? They're able to sort of put something down if they feel is correct here and willing to share with the class. Let me check the chat. I'm sorry, I saw that we had. All right, good. For fission. Anybody have two forms of energy released in the reaction? Anybody? So one of the forms of energy that we talked about was that when you split apart uranium, each one of these things is going to, it's like an explosion. They're going to sort of fly apart with velocity. And if they have velocity, they have kinetic energy. So kinetic energy of, and let's use the language that's up there on the chalkboard, the fragments. And so these, the lanthanum and the molybdenum are the fragments, but you could say the products, kinetic energy of the fragments. So these things are going to have velocity. They're going to be moving. If this starts with a stationary nucleus, then these are moving, right? Then some of that energy is showed up as kinetic energy of the particles, of the fragments of the product. And then the other one that we talked about is that in all nuclear processes, we will create gamma photons. Okay, so high energy light. So the gamma decay is like when you got a really energetic nucleus that just emits a photon out of it, it becomes a little bit more stable. It loses some energy in the form of gamma photons. So that's a type of decay on its own, but it's also going to be something that's sort of created within these reactions. So you can kind of say like there's an extra gamma, kind of looks like this, kind of like a fancy looking Y. Okay, so a gamma photon. All right, because this is a 7-mark quiz, we want to get it up to 10. Okay, so we're going to give ourselves, we're going to take our 3.3 by 10 to the negative 11 joules that we had up here. Now go ahead and take a few minutes to try to convert this into mega electron volts. Okay, so from joules to mega electron volts. See who can't reference their notes and say, oh yeah, we did that. You know, we turned joules into mega electron volts. And so this is going to be a chance for some extra credit. All right. So that we can get this up to 10. So we got a 10-mark quiz this Friday. I'll give you a few moments to get a head start on the calculation, and I'll show you what it looks like. Let's see, still got plenty of time. All right, was that enough time for you to convert it into mega electron volts? If not, then go ahead and pause the video at this point, take as much time as you need, and then hit play when you're ready. If you're live in person, sorry, you can't like pause reality. You're just I'm gonna go through the answer now, but if you're watching this on YouTube later, you could. All right, joules is what we want to cancel, so put that down here. Like just let the units guide your calculation. Like I don't want to be in this unit, so I'll put it down here so it cancels. I want to be in, I'll just go to electron volts first. Hopefully you have it in your notes that there is 1.6 by 10 to the negative 19 joules per electron volt, okay? I want to show you, I still have this number in my calculator, the 3.3 by 10 to the negative 11. Here's what happens if you don't use parentheses when you go to divide a value in scientific notation. So let your eyes adjust. There they go. So if you don't use parentheses, here's what happens. divided by 1.6 times 10 raised to the negative 19 equals, you get an answer that is 2 something by 10 to the negative 30. Very, very incorrect. We're dividing by a small number. So I'm going to take my 3.3 by 10 to the negative 11, right? So that's the number I have my numerator, divided by, open parentheses, 1.6 times 10 raised to the negative 19. When I close the parentheses, I see, yep, that's the number I wanted to divide by, that really, really tiny number, which gives me a big answer. So I have 206,250,000 electron volts. When you do 3.3 by 10 to the negative 11, when you type it in without parentheses, you're dividing by 1.6, and then you're multiplying by 10 to the negative 19. Okay, so instead of dividing by a really tiny number, you're taking 10 to the negative 11 and you're multiplying it by like another 10 to the negative 19, which is why your answer is way, way wrong, right? Instead of getting a big number like this, you get a number that's very, very small. So you must use grouping symbols when you divide by a value in scientific notation. Otherwise, the calculator just follows the order of operations. It multiplies and divides from left to right. So it does the division first and then the multiplication. It knows to evaluate the parentheses and say, okay, do this. This is the thing I want to divide by if you use parentheses, right? So this is the correct answer. To get it to mega electron volts now, you take your, there's different ways to think about it. So you could just say 206,250,000 electron volts, and you know that a mega electron volt is 10 to the 6 electron volts. In other words, this mega means 10 to the 6. So just dividing this by a million means we're going to move the decimal point over, 1, 2, 3, 4, 5, 6. So you'd have about 206, if you want to have the 0.25. You keep it, you can just round it, about 206 mega electron volts. The other thing you could do that we talked about the other day is looking at sort of a number like this. You can say, well, these sort of 6 place values here is like times 10 to the 6. So this is like 206 times 10 to the 6 electron volts, and 10 to the 6 means mega. So that's another way to sort of get, that answer. It just depends on what you're more sort of comfortable with, converting. You say like, oh, okay, there's 6 orders of magnitude, that's a mega. Or I just like to set it up very formally like we did here, canceling out the units, that we don't want to be in, getting to the units we do want to be in. Some sense of satisfaction in sort of doing these. You cancel out what you don't got, and you get to where you want to go. This has been a nuclear fission reaction with Dr. Schleich. We'll see you next time.